AP Calculus, Teacher Tiberio, 5th semester, Prepa Tech. Judges, Diego and Roger present the math project from the first partial. Read and understand the problem.
Identify each variable. Define volume and cost equations.
Apply derivative to optimize the problem.
Teacher,
Done!
yay!
Get your game on, go play. Hey now, you're a rock star. Get the show on, get
A rectangular storage container with open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of the materials for the cheapest storage container. And that's our problem! Oh yeah, man! We made a diagram to represent the storage container with its respective measures. As you can see here, here's the weight, here's the length, and here's the width. And we put its respective measures or values for all variables. As you can see here, volume, as it was given in the problem, it's 10 cubic centimeters. The length is twice width. Width is equal to width, and height is equal to height. So, as we know now, the formula of the volume is length per width per height. So, as it was given before in the problem, we substitute the values that we already have, and we substitute it in this formula, obtaining this. 10 equals twice width per height. Finally, we just simplify that measures to obtain this expression. 10 equals twice width squared per h, and then we isolate for h. h is equal to 5 over width squared. So, after all of this, we put the things that we already know in the function form C of w. As we know, the storage container is open, so we know that 10 is the price in dollars of length per width. So as it is open, we're just going to use one side of the container. Then we know that two containers cost $6 per width per height, and then two containers cost $6 per height per length. Finally, we just simplify that expression with values that we already know, like in here. We substitute from which values? From the ones that we obtained already in our formulas before, on the values of the variables. Then we simplify this expression and we obtain that C of W is equal to 20 W squared plus 180 W elevated to the minus 1. Later, we obtain its derivative, and we obtain that the derivative of C of W is equal to 40 W minus 180 W elevated to the minus 2, that this is actually equal to 40 W cubic minus 180 over W squared.
We obtained the derivative of the function. We found the critical numbers if and only if C of W is equal to 0 or does not exist. We equalize the derivative of the function to 0, and we isolate W in order to obtain the other three variables. In this equation we find the value of h, and in this the value of L. Replace the variables in the function in order to obtain the cheapest cost of the material to the rectangular storage, and that cost is equal to $163.8.
That's perfect.
The teacher. We obtain the critical points and verify by substituting these values in the C prime equation. The C prime of 0 gives us do not exist, that at the same time is a vertical asymptote, and C prime of 1.65 is 0. We take these test values to see the behavior of the graph around our critical points.
So, for the critical points that we have, we obtain three different intervals. From minus infinite to 0, from 0 to 1.65, and from 1.65 to the infinite. Then we just made the value test, the test value, using these values minus 1, 1, and 2. So we substitute each point in the derivative, obtaining as results minus 1, 1 that are pointing downward because of the sign obtained at the result. Then we obtain that 2 is going to point upward because the result of substituting this value in the derivative is positive. And finally, we can say that 1.65 is a minimum value. So as we said before, we have our critical points that were 0 and 1.65, and for each critical point we were going to have 3 intervals. Like for example here, from minus infinite to 0, from 0 to 1.65, and from 1.65 to the infinite. And we obtained that 1.65 is a minimum value because here the value of 1 it's pointing downward, and when it's 2 it's pointing upward. We know this because we replace both values in the derivative function, and then we know that it's going to make a curve, it's got a concavity in 1.65.
Name is John C.